Good day, everyone. Welcome back to the channel. In this video, we will be beginning a new topic, which is one of my favorite topics in grade 12 math. The topic is calculus, as you can see. Main reason why it is actually my favorite topic, it's because when you go to university and you study these courses that involve math, calculus will be your main topic. Basically, your whole math in university will be based off calculus. Obviously, there's statistics and other types of math that you're going to be doing, but the whole purpose of math in university is literally calculus. Okay, there's a very extensive topic, but obviously in matric we just get like a brief introduction of it, and that's what I'll be aiming to teach you in the next coming videos. So without wasting any further time, let's get straight to the video. Okay, so in this example, we're told to calculate the gradient of the following. So we're given a straight line and we're given 2 points, which is -3 and 2. And with that information, obviously we know that these are the points of interception. So we have all the coordinates that we're going to require or need to be able to calculate the gradient of the line. And from what we've learned, we know that gradient is basically calculated by us saying m is equal to fx2 minus fx1, all that over x2 minus x1. And if we substitute all the points or all the coordinates, here we know that fx2, we're going to call this one fx2. So we know that that will be 2 minus, and obviously x here will be 0 since it's intercepting the x-axis, all over. And then we know that the coordinate of x at that point where y is 2, it's 0 since it's the y-intercept, and the other one will be minus 3. Okay, so if we substitute everything, or if we clean up this here, we're going to end up with 2 over 3. So the gradient of this line is 2 over 3. But the main thing that I want us to basically understand is that for us to be able to calculate the gradient of this line, we needed 2 points. All right, we needed 2 points, and that's how we're able to calculate the gradient of this line. So now, what if we're given a scenario like this where we have a graph, a cubic graph, and we're told to calculate the gradient of the graph? That would be very difficult because the gradient of the graph basically changes throughout the whole graph. So the gradient at this point would obviously be 0. The gradient of this at this point would obviously be different. The gradient at this point would obviously be different, and obviously the gradient at this point would be different. So we can't really determine what the exact gradient of this graph here is, but what we can do is we can try at least to look at 2 points to kind of determine the average gradient of the graph. And in this case, we can draw a secant, which is just a line basically that intercepts 2 points of the graph, and in this case it would be that point and that point, and calculate the gradient of that graph. But then again, this line still doesn't determine the average gradient of the graph, because if we do draw another secant looking in the opposite direction, let's say we draw another secant like that, this gradient would definitely be totally different from the gradient that we drew the first time, or from the line that we drew the first time, because these are 2 lines looking at opposite directions, and they will totally have different gradients. One will have a positive gradient and the other will have a negative gradient. So how do we go about trying to determine the gradient of such a graph? Remember, when we're calculating gradient, we're basically looking at a change in y over change in x. So as I've already mentioned, in order for us to calculate what the gradient is, we're going to need 2 points. So what essentially calculus does is that it allows us to be able to calculate a gradient at a point. So instead of having 2 values of x, or instead of having 2 points in order to calculate the gradient, we can just calculate the gradient at a certain point. And let's say, for example, that point would be that. And if we were to draw a line that basically intercepts that point, that line would obviously be known as a tangent, as it only touches the graph at one point. So if, let's say, for example, we're to fill in the coordinates and we're to say f of x, obviously x will be the same since it's 1 point, minus f of x, all that over x minus x. Then essentially we're gonna have something like undefined, as x over x will be 0, and obviously that gives us a gradient of 0, or undefined in this case. Actually will give us 0, since f of x minus f of x will also be 0. So we have 0 divided by 0, which is 0. So we seem to get nowhere. So with calculus, we introduce something called a derivative. And what a derivative basically does is that we assume that in this secant right here, which is basically this straight line, these 2 points over there, let me try to erase that. Oh, I managed to erase everything now. Those 2 points over there, we assume that they're getting closer and closer together, but obviously they never become one. So what I mean by that is that we're going to assume that this point here would obviously be x, and we're going to see plus h, and the other point we'll call it x. So now if we were to use our gradient method, we're going to say f of x plus h minus f of x, all that over x plus h minus x. And if we simplify that, we're going to have f of x plus h minus f of x all over, and the x's will cancel out each other and we only have h. And that over there is what we call a derivative. And this derivative is what will allow us to be able to calculate the gradient at a certain point. So instead of us calculating the change in y over change in x, we're only calculating the gradient at one point. So the standard way of rewriting or writing this is for us to say f of x, or the derivative, is equal to f of x plus h minus f of x all over x plus h minus x. But remember, these 2 points, which is x plus h and x, we're assuming that they're getting so close to such a point where they are now one. They are not far from each other. By the looks of it, they are far. But what we're trying to do is we're trying to bring them so close that they look or they seem like they're at the same point. So in order for us to be able to do that, we need to now integrate h, or we need to assume that h is equal to 0. But now we know that these x's are going to cancel each other, and what we have remaining here is f of x plus h minus f of x, all that over h. And if we were to substitute the h at this point, then our graph will be undefined, or a derivative will be undefined. So what we're going to try to do is we're going to try to find values and substitute here on the top part, or I'll say on the numerator, and then try to find a way to factorize h so that it can cancel. So now let's jump at an example and see how we can apply that first principle derivative method in order for us to calculate the gradient at a certain point. So here we are given an example. We are told that f of x is equal to x squared, and from that we're told to calculate or determine the derivative, which is represented as this, using the first principle. So if we were to visualize the graph that we're given, we know that it's just a parabola. So it will be a parabola like this. And remember, a derivative basically refers to a gradient at a point. And obviously, the gradient at a point changes all the time. So the gradient here at this point will be different from the gradient here, will be different from the gradient here, and it will be different from the gradient here. So now we'll be able to use first principle in order to formulate a formula that would allow us to calculate a gradient at a point, only if we can substitute the x value of that point. So now, to do that, we need to use the first principle. So the first principle basically says f of x, h is 0, equals to f of x plus h minus f of x, all that over h. So f of x plus h basically means that where there's x, we need to substitute by x plus h. So let's do that. So from the formula here, we're going to substitute x with x plus h, and we're going to square that, and we're going to say minus f of x, which is x squared. So since it's one term, I'm not going to put a bracket. All that over h. So now, if we further simplify this, we're going to get x squared plus 2xh plus h squared minus x squared all over h. And if we look for like terms, we have x squared and x squared canceling each other. So another thing to always remember is to always carry this until you're able to substitute your h as 0 or your h as 0. If you don't carry that, you're most likely to lose a mark. So to further simplify this, while carrying this, it used to annoy me having to carry it everywhere when I was in high school, but it was necessary. So to simplify this, we have 2x plus, sorry, not 2x plus, we have 2xh plus h squared all over h. And from the numerator, we do have a common factor of h. We're going to factorize that. Now we have 2x plus h remaining all over h. And let's not forget to carry that with everywhere we go until we substitute it. So now we have this h and this h over here canceling each other. And what we have remaining as a final answer is 2x plus h. And from here, we're still carrying this with. So now in the next step, we can substitute h as 0. And if we substitute h as 0, we don't need to carry it anymore. And our final answer will be 2x. So the derivative will be 2x. And what this basically means there is we're able to use this right here, or the derivative, to calculate the gradient at any point. So the gradient will depend on what the value of x would be. So if we go back to the graph, we know that the gradient that looks like that, obviously that's a secant, it's not a tangent, it's supposed to be drawn as a tangent. A gradient that looks like that will be negative, and a gradient that looks like that will be positive. So we can only substitute a negative. As you can see, it lies on the negative side of the value. So the gradient will obviously be negative if we substitute x here as that x value, or that as that negative x value. So that is the power of calculus. It allows us to be able to calculate the gradient at a point instead of needing 2 points and trying to calculate the average gradient like we always did in the past. So this is what we use. We use the first principle in order to calculate that. And we're going to try to do one more example to kind of integrate that knowledge. So in this example, we're given the following function, f of x is equals to 3 over x, and we're told to calculate the derivative using first principle. So to do that, we need to say f derivative h is equals to 0, h is 0, and then we write down the formula, which you do not have to memorize, as I've already mentioned, because it will be given to you in your formula sheet. So now, the only thing you need to do is obviously substitute x plus h where there's x. So here it will be x plus h minus 3 over x. All that over h. And let's not forget to carry this throughout the whole time until we manage to substitute it, or substitute h at the end. And from here, we can just find our LCD or LCM. And our LCD is x plus h multiplied by x. All that, and then we're obviously just going to cross multiply. And if we do cross multiply, we have 3x. And on the other side, we have minus 3x plus h inside brackets, just like that. Remember, everything is still over h. I know this might be a bit confusing, but if you did your fractions back when you were still in grade 8, grade 9, I'm sure you'll be able to follow through. So let's not forget, we need to carry this until we substitute the final value. So even here, we need to carry this, or else it will be wrong or we'll lose a mark. So to simplify the top part, we have 3x minus 3x, sorry, that's not plus, that would be minus 3h. All that over x plus h and x, and then over h. So from here, what do? These two cancel out, and at the top we have minus 3h over x plus h times x, all that over h. So just to clarify, or to make it more simple, let me not forget to carry this with every single time. Even here, I'll carry it with. So to make this more simple, I'll rewrite this as, and then instead of me writing down the h there, I'll just say divided by h. Okay, and here we'll just flip and times multiply by, and we're going to have 1 over h. Let's not forget, we need to carry this all the time. Sorry. We need to carry this all the time until we substitute. So this will cancel out with this. And what we have remaining, let me just open a new page. We have f of x h0 equals to minus 3 on the numerator all over, and if we multiply the denominator, we have x squared plus hx. So the last step is where we substitute from here, and if we substitute that, we're going to have minus 3 all over x squared plus x, and we substitute 0 as our h. So our final answer will be minus 3 over x squared. So the derivative, or the average general gradient at a point, it's not even the average general gradient, it's the gradient at a point. The formula for that will be represented, or the formula for that is this over here. So that is the concept of the first principle, which is us basically calculating the derivative. And as I've mentioned, the derivative allows us, or is us basically calculating the gradient at a point instead of using 2 points all the time, like we've always used 2 points. So that is it for this video. I'm not going to make it more longer than it is. I hope these 2 examples were able to explain what first principle is all about and what it is used for. So I will see you in the next video. Please don't forget to like, share, and subscribe. Cheers.